Michelle Bangert, Managing Editor of Quality. We're here today at the MAX event in Nashville with Dilip Shah. He's the president of the E equals MC Cube Solutions, and he'll be presenting at the show about calibration. So Dilip, welcome. Thank you for being here today.
Thank you. Glad to be here.
Yeah, we're glad to have you. So at this session, you're going to talk about calibration reports. Can you tell us a little bit about what your session will discuss?
Yes. So my session is going to talk about how do you assess a calibration report where you calibrate something to a nominal value and you compare it to a specification or tolerance. And traditionally, if the measurement's within the tolerances, that's considered a pass. If it's beyond the tolerance limits, it's a fail. But now you have a thing called measurement uncertainty associated with making that measurement. When you take that into consideration, now you have four possible scenarios: pass, fail, conditional pass, conditional fail. And so what it says is that there may be a certain risk associated with making any one of those four statements of conformity. And then there are different decision rules associated with making that conformity statement. And different decision rules have a different risk built into those decision rules. So it gets a little bit more complicated than that. For example, let's use a tire pressure gauge. The tire pressure gauge could be used to check your bicycle's tire pressure. When you use it for that, and let's say it's not right and you underinflate your bicycle tire or overinflate your bicycle tire, that risk, the worst you could do is like you could have a flat tire, you may fall off your bike, but you could get out of it. So there's very minimum risk. The same tire pressure gauge, you check your automobile tire pressure on the tires. And that may have a little bit more risk associated with that. Now imagine using the same pressure gauge, checking the tire pressure of a passenger aircraft jet. And you could see the same gauge, different risk, making that statement of conformity. So one decision rule may apply to checking the bicycle tire pressure, and a different, tighter decision rule may apply to a passenger jet. And that's what calibration involves. What has happened is technology is evolving so fast that the standards used to calibrate that tire pressure gauge, they can't keep up with the better tire gauges you have. Now, I have a story. Several years ago, I bought 4 cheap tire pressure gauges from Walmart. They're $5 a piece. And then the metrologist got into me. So when I brought it home, and I said, I wonder if they all read the same. Now, I didn't have a standard at home, but I had an inflated tire. So I said, if I check them, they should all read the same. Guess what? Between the 4, there was a difference of 7.5 PSI. And that's a lot.
Yeah.
So I said, obviously, I'm not going to use these gauges. But since I train in metrology, I said, I'm going to keep this. It'll be like training aids to show the same concept to students. And then I ended up buying a Michelin digital tire gauge with a resolution of 0.1 PSI, and then check them against my standard, the inflated tire, and they were within 0.1 PSI. So you could see the risk with that Walmart pressure gauge versus this, $15 pressure gauge that I got from Amazon. And so that's a great way to, differentiate between, you could have the same instrument with different accuracies, different uncertainties, different resolution, And all of those contributors play into the measurement uncertainty. Now, from a layman's perspective, measurement uncertainty is basically all the errors associated with your measurement. And those errors could come from the environment, the resolution of the device. The Walmart gauge was analog, obviously. The Michelin gauge was digital. Um, the person using their technique, and their accuracy specification and everything. And so, in a nutshell, I'm going to talk about it's no longer a simple pass or fail, and it's about taking the measurement uncertainty into account and then using a decision rule to say whether it's a pass, a fail, conditional pass, conditional fail, and whichever one of those four decisions you make, how much risk is associated with that. And that risk is normally called PFA, which is probability of false accept. And there's tools developed for that. And that's what I'm going to talk about in a 15-minute time frame. And obviously, I teach same kind of thing in a 5-day workshop, but I'm going to put it in a 50,000 feet Reader's Digest version.
I see. Makes sense. So in her workshop, Heather Wade mentioned your idea of the bliss of a single measurement. So can you talk more about that?
I should probably patent that
It's
somewhere.
a great phrase.
So the single measurement bliss is usually when you calibrate something, you make one measurement. Now, when you make that one measurement, you put all your decision making into that one measurement. Now, there's a 50% chance you're right, 50% chance you're wrong, but you don't know. So that's where the bliss part comes in. But I also say bliss is ignorance in disguise. Okay? Because what we don't know, we don't know. So you make a second measurement as different than the first one. So now you introduce doubt in your measurement. And then you say, okay, I'm going to make a third measurement as different than the first and second. So now you introduce more doubt in there. Then you say, okay, you know what? I'm going to make a fourth measurement. And guess what? It's different than the first, second, and third measurement. But then what you end up doing is you made repeated or replicated measurements. And then you say, okay, I'm going to use basic statistics. I'm going to average those measurements. And then you say, I think when I make any one of those measurements, it should average around that average value as long as I have certain variability associated with that. And that variability, which would be the variability of four measurements, and you can look at it and say, this is the range, or if you wanted to be a little bit more technical, as the standard deviation. And that's really uncertainty in a nutshell at a very basic level on that measurement.
Yeah, that makes sense. It's a great example to show, like, you have one, you feel good. You have three, you feel a little less.
Yeah. And, you could go and make the fifth one, sixth one. But there comes a time where there is utility of making too many measurements. And at some point, it's not going to give you any more information depending on what measurements you're taking. And Walter Shewhart was the inventor of control charts. And, he invented control charts back in 1924. So here we are 101 years later, and still very great concepts. And one of the things he talked about in the X bar R chart, where you took so many repeated measurements in a subgroup size. And he says the subgroup size should be usually anywhere from 3 to 5 in a subgroup measurements, and you average that. Any more, he used the term relative efficiency. That means you're not going to get any more information if you make five or more. And that was very practical because originally the control charts were used in a manufacturing environment, and you're making hundreds and thousands of parts, and there's really no time to make that many repeated measurements. So usually you can make 3 to 5 measurements, average that, and then sample that at a certain frequency, and you get some very, very good information. So in that perspective, to me, he's my hero, by the way. But because he was a genius. Back 101 years ago, we didn't have calculators. We didn't have, and these folks that were using the controls chart, they weren't mathematicians or statisticians. So he made that complex subject very simple. And so you take an average, take a range, which you can easily do, and then get some very, very useful information out of that. And I say that, this was in 1924. In 1941, we entered the Second World War. And Schuhart's method was one of the other silent heroes that helped us win the World War by producing some really, really good hardware to fight in Europe and Japan uh, in there. So these are techniques that we kind of think they're new, but they're not new. But since then, we've found a lot of different ways to use them. No longer used in manufacturing. I mean, they're still used in manufacturing, but we've applied them in many, many different sectors. And metrology is one of the ones that I've really pushed for use of those tools, and they've been very, very useful in those things. So sometimes what is new is not new in quality.
Yeah,
It's just that you apply it in different industries, or you apply it in a different way, and so that's nice.
Yeah.
The science, in some ways, doesn't change.
Yeah, that's interesting. I was going to ask what how measurement science has changed, but like you said, there's some things that are really evergreen and still very useful and relevant. So that makes sense. I know you're really a technology guru and interested in all kind of new things. What's kind of the latest technology you've been interested in?
Yeah, so technology has always been my passion. Ever since I tore apart my mom's electric sewing machine when I was 5 or 6, never put it back together. So when I got my first paycheck, I bought her a brand new sewing machine. But there is so many areas where technology is evolving that it's really hard to keep up with all the areas. So obviously, where your interests are, you look at and say, what is changing? And obviously, in metrology, the area I work in, the standards are getting much, much better. And so that's one area. And then the other area, like photography. What's happened in technology is the mating of the hardware and software has got much, much better. I mean, you look at your smartphone and you take a picture, and that picture is perfect. You could have a $1,200 camera, and you can fiddle with all the settings, and you may not get the best picture. But here's that smartphone makes all those decisions and does that for you. So, we talk about AI, but AI is already built into some of those things and so on. So I'm just fascinated by the imaging part of it. And so in the photography, and obviously that photography goes in the imaging, and that the shot today, there's a lot of imaging that's using AI. And from the personal point of view, you have 360 cameras, and I've got a couple of them, and I'm playing with them. And so now you don't have somebody to take your picture where you're somewhere, the 360, will stitch that image, and you can look at it from any viewpoint that you want. So there's nothing like taking a selfie. It does the whole thing, and the software, you can define whether you want it in front of you, behind you, over you, sideways, and so on, like that. And then the same kind of technology is going to get built into calibration things. Now, one concern about technology as it evolves is we made great advances, microelectronics and so on, but the reliability is one that is a concern. Uh, what's happened is when electronics get miniaturized, we have surface mount technology and so on, and then we have environmental rules about soldering, and the soldering that's used in surface mount technology is soldered at lower temperatures. And I think the robustness there is a concern. So a lot of the new technology that's coming out, it's really advanced in technology, but from the reliability side, a lot of times it fails. So that I see as a challenge and say, how do you, still increase the reliability? Because there's a company that makes 8.5 digit multimeters. Same model and make they made 35 years ago. And I've got client labs that have that same model and still is working, 35 plus years old. And they buy the same model, same functionality, same model number. And the newer units are not as reliable because the electronics inside is surface mount technology and so on. So I see that as a challenge.
Yeah.
And that is my perception. So, being a quality professional is one of those things where you can't think in a silo because your root causes can come from any different areas. So you have to be a pretty well-rounded person, or you should strive to be a well-rounded person as a quality professional. And it's not like, okay, I'm gonna be in a quality profession in electronics or in mechanical testing. You gotta know all the disciplines. Not everything well, but you gotta know enough to make the connections, because in quality, you're always solving problems and the root cause analysis. If you just put blinders on and look at it from this point, you're not going to be able to do that. And that's a challenge for a quality profession. And so you can't like go and take a degree in quality. You got to have a degree in disciplines. And even within the disciplines, which used to be pretty rigid, you became an electrical engineer, you became a mechanical engineer, you became a civil engineer. Now there's a little bit of a creep, a seepage in those bodies of knowledge. And that is good because you do need that. So you are not thinking in silos and you know a little bit about this. So when I talk about the reliability of this electronics, I know about the thermal shock and the surface mount, the solder, lower temperatures, and so on. So it's not just soldering, it's what kind of soldering it is, what kind of connection, what kind of thermal stress is in there. So I see that as a challenge in the quality profession, because quality professionals evolve quite a bit in the sense that you're not in that quality control, you're in quality assurance. And in there, you have to have an open mind and not think in, I call isolated thinking. You gotta be in that consolidated thinking, that you have to have different knowledge in every areas.
That makes sense. So I think those are the main questions I had for you today, but is there anything else you want to mention or things you think we should include now?
Um, of course, I can talk for hours about things, and we never have time to do those kind of things. But I'm always very happy to be at any show, any conference, and I'm always excited. And I'm an optimist, and when I see this technology is evolving, and I feel good that the world is moving in the right direction in a lot of ways. Obviously, we have a lot of problems, but at least in these areas that I work in, that people are moving in the right directions. And so it's always a pleasure to come to any of the shows, the assembly show, the MEC show, the other measurement conferences I go, that things are moving in the right direction. People are networking, exchanging information, and the best thing you could do as a humankind is sharing of the knowledge to benefit humanity. In my small way is the way I look at it. So it's always a pleasure, and I get so hyped up when I attend any of the shows and leave, and then like I said, oh, that it's over.
Yeah.
It's like too short, you know.
Yeah, yeah. Well, thank you for sharing that. We're definitely glad you're here, and that's such a great optimistic view and kind of big picture concept. So I appreciate it.
Thank you. Thanks for having me.
Okay, thank you everyone for listening, and we'll see you next time.